Oh, that's not what I meant. All right. Hello and welcome, people in TV land. Today is Tuesday, December 13th. I want to remind everybody that at this point you should have your phones put away. You should have your AirPods and your earbuds out. And you should have your notebook open. And you should be writing down the daily question. So if we look at the daily question up here, it says, how do you think convection currents move the crust? How do you think convection currents move the crust? If you could please write that down, I would greatly appreciate that. If we look at our agenda, we're going to do our capture question. We're going to talk about some convention notes, and so that'll be like the third day that we are talking about convention. And then we're going to do a little work on Pangea. How many of you have ever heard of Pangea? Okay. How many of you have ever heard of Rodinia? Okay. Today, content objectives. Students are going to investigate and model the movement of the crust due to convection currents. How are we going to do that? Well, students will construct a model of continental separation and the ancient supercontinent Pangea. Students will be able to explain Wegener. I know that that's a W, but we say V as in victory because it's German. Wegener's theory of continental drift and the evidence used to support this theory. I want to remind you of some upcoming events. Your PBS Thermal Energy Project is due Wednesday for all people except for Justin. Show me your ears.
What?
You're not a stupid man. Show me your ears. Thank you. Get them out. Other one too. Thank you. So your thermal energy project is due Wednesday for everybody but Justin, and you're going to have a quiz this Friday. We only have one more week after today, and then we go on some winter break. So I'm excited about that. And it's a long winter break, it feels like. We are going not to come back until the 9th. So that's a very long break. I know, we all need a little bit of a pause, so it's going to be nice. Did you have your phone out? Fidget. Good for you. I'm going to get myself one of those. Let's go ahead and be quiet for Mrs. McGrain. I'm going to shut my mouth, which is difficult for me to do for 1 minute. And if you could please turn with your pair share partners while I take attendance. And we're going to be talking about this question. Would you mind sharing with Logan? Okay, says it all. All right, so let's go ahead and if you could please write something down, and if you could talk with the person next to you, I'd greatly appreciate it. I'm trying to set, yeah, and I'll take attendance. So turn and talk to the person next to you about continental drift, please and thank you. Justin, what were you studying at West? Has anybody seen Billy? It says that they are in the building. Not here today? Billy sits next to Logan. Everybody seen Hassan? Well, we're just dropping like flies here as far as our numbers. Flu's going around. Gotta be careful with yourself. Everybody get their flu shot yet?
I did.
Yeah, me too. Flu shot. Flu shot? Yes. Get your flu shot. Alex, you get a flu shot yet?
No.
Oh my God, you're wrestling with people in close contact?
I haven't been wrestling this entire week.
Okay, but what I'm saying, like, you maybe have gotten sick last week. You know what I'm saying? I'm just saying, given your occupation or profession or hobby as a wrestler, it might not be a bad idea to get a flu shot. All right, let's go ahead and share out. Could we please, how do you think convection currents move the crust? First of all, where do convection currents happen? Mantle. Okay, let's start there. William, would you mind turning it this way, please? So we've got number one. You got to have something happen in the mantle. And so convection currents. Okay, so in the mantle, we have convection currents. Fabulous. So what? What happens with them? Oh my heavens. What happens? Who cares if there's convection currents in the mantle, and how does that move the crust? If all you know is, yep, convection currents, then we are in a sad state right now. So convection currents, what do they do? Yeah.
They rise up.
They rise up, they move, and they fall sound, right? So convection currents rise and fall due to what, William? Why does a fluid material rise?
Heat.
Okay, heat is what brings it, that's right. Heat changes what about it?
Density.
The kinetic energy.
Okay, kinetic energy, that's right. So rise and fall due to, how about this? I'll say temperature changes that drive density. It's all about the density, baby. Temperature changes that drive density. Ethan, write some of this stuff down. All right, so we've got the crust, and we've got the mantle, and we've got these convection currents. Here, I'll do them like this. You got these convection currents that are moving, let's say, like this. All right. And then underneath the mantle is what?
The core.
The core. And so that's where the heat comes from. I'll say core and heat. All right, so that's where the heat comes from, and it changes the density that makes that mantle rise, or up here is cooler, so I'll go ahead and write cooler up here. So we have temperature differences that is changing the density. Fantastic. So what? What do those currents do then? I know they rise and fall. But then what happens? We're still talking about how it moves the crust. What must be special about those currents then? What do you think, Asa?
The currents are strong enough to slightly affect the crust.
To what?
To slightly affect the crust.
Okay, how are they affecting the crust?
Moving.
Yeah, they're moving them. Why is the magma moving the crust? Why? What is it you think about magma that moves the crust? High five. What is it about magma that moves the crust?
Sticky?
Sticky. That magma is really sticky. So we got this sticky magma that attaches itself, right? It's at the bottom of the crust, if this was crust, right? We've got this situation right here, and these currents are moving. How are these currents moving in that picture? Towards each other or away from each other? They're moving towards each other. So if this crust is being pushed towards each other, what do we think is going to happen in the middle? Yeah, probably we're going to have like some sort of a little mountain range or something. And it's sticky, right? It's very sticky, viscous substance. And so what we've got is we've got this sticky mantle that is attaching itself to the bottom of the crust, and you get like this slab push, and you get this slab pull. Do you remember reading about like push and the pull of the slabs? Ridge push, slab pull. Okay, so that's what we have happening here. Oh, gross. Will you help me? Just kidding. I know you were, and that makes you a good person. All right, so mantle, convection currents rise and fall due to temperature changes that drive density. And what happens is this mantle, right, this magma is sticky. So we got this sticky magma in the mantle that pushes or pulls the crust towards or away from, I guess, each other. Those are plates. We have these big, huge crustal plates. Awesome. Now, in this case, because they're coming towards each other, think about these big gears. Like this is turning that way and that's turning that way. In this case, we would have like these mountains that would be created right in between as they're crushing together. Think about like a beautiful big black SUV. and then another one, exactly the same density, the same size, and they slowly come towards each other and they don't stop when they meet. What's going to happen to the front of them? Yeah, they're going to get all crumpled up. That's what's happening right here. We're crumpling the crust as it's coming towards each other. So the crust is moving in this way and in this way because of the way that the currents are happening down below. And that's where we get, like, you know, these beautiful kind of like mountains and whatnot that are created. Like the Himalayan mountains. Anybody ever heard of the Himalayas? Yeah, and so that's how the Himalayan mountains are created. All right, so that's just part of it. And we're going to go ahead and study that today. We're going to look to see, how do we know that the crust has been moving for like millions of years? And that's going to be an activity we're going to do today with reconstructing Pangaea, which was an ancient supercontinent. But before we do that, we're going to go ahead and take some notes on convection as just like a little review. I'm going to go ahead and wash this off my hands. If you could please get your table of contents out. And my good friend Justin needs a table of contents. So I'm just going to pass this down. Can we pass that down and back towards Justin? And I will wash my hands while you all get your table of contents out. I would never do that to you.
Yeah.
So disrespectful.
Yeah.
Never. What? I did what?
Touched corn syrup? Corn syrup isn't going to hurt me.
Just for demonstration.
Demonstration purposes. Corn syrup is the closest thing that I can think of to magma without actually creating magma and like hurting myself and like, no, I'm not going to do that. All right, really quick, I got to get something out of the refrigerator in order to get us started with these notes. All right, got some blue water here. Now, typically, if we have blue water, what should this temperature be? Ah, no. In science terms, what should this water be? Hot. Do you have your phone out? Show me your hands. Lies. Give me your phone. I love you so much. Give me your phone, and I don't want you to jeopardize your success. I'll put it right up there, and you can have it at the end of the class period. Excuse me. You are. I care about you so much that I don't want you to jeopardize your success. I'm going to put you in number 20 because I envision that when you're 20 years old, someday we're going to run into each other and you're going to be like, Miss McGrain, remember that time? All right. So, in terms of electromagnetic radiation, blue should be what temperature? Hot, right? But where we are kind of like in our society, we don't do that. All right, let's go ahead and set up our TOC, table of contents. I'm going to go to, here it is. Now, Justin, these are the two things that we've already handed out. I'll make sure that you get them. But if you could please turn that over. We are filling out our table of contents. It's just like a table of contents for a book. I bet Mr. Pujol has table of contents also in West. Okay, so then today's date is 12/13, and we are going to be doing some notes. And these notes, I believe the top of it says heat transfer. Is that right? All right, now, on Friday, we did a little reading about heat transfer. That's your essay that is due on Wednesday. And again, I've got some sheets of paper up here to help you with that if you need it. Also, on today, 12/13, we are going to be doing a lab, and that lab is called Reconstructing Pangaea. We're going to start it today, and we are going to finish it tomorrow. Notice the spelling of Pangaea. Pangaea. That old spelling. Maybe some hand sanitizer. That alcohol will cut right through it. All right, are we good? Good? Okay, and if not, your pair share partner right over there. Which, do you not have the new one? You just keep adding to the old one? Okay. You know, we're not doing that anymore though, right? So So here's your heat transfer and convection currents. Heat can be transferred to another object in 3 different ways, and you've already learned about these based on that work at your own pace PBS learning. We've got conduction, we've got radiation. I believe in the PBS it was called thermal radiation, and then you also have convection. And we've done a lot of work on convection. This is going to be our sweet spot for when we're talking about plate tectonics. So I'm going to open up this PowerPoint, and you are going to go ahead and fill in, and I'll show you where to fill some things in. And I'm going to change a little bit about what they do, because I think that what they do is just very kind of like grade schoolish, and I want to add to our level of understanding. So our first idea for convection inquiry: what will happen when you mix water with 2 different temperatures? And so I have got, it's actually cold because I've got some blue ice cubes that I froze, so I'm going to fill this up with blue cold water. All the way to the very tippity top. And then I'm going to go ahead and fill this one up with warm water that is spilled all over. That's really hot. So with your pair share partner, when I tip this over and I put one on top of the other, tell me what you think is going to happen. Try and talk that out. Did you just say I don't know? What do you think is going to happen? Would it matter which order I put them in?
Yes.
Okay, so let me go ahead and start with, I'm going to put the red on top of the blue. I'm going to put the red on the top of the blue, and you tell me what's going to happen. Go ahead, talk that out before I do it. Oh. What's going to happen? Red's going to stay. Red's going to stay on the top, and the blue's going to stay down below. Why do we think so?
Heat rises.
The ice cube went up. The blue ice cube is, I can see the blue ice water melting and falling down. Well, that's kind of a bust. What if I switch it? Now what's happening? The red is rising, and I see blue sinking. It's all about why? Why is that happening?
Because heat.
Density. It's all about density, yeah. Because the heat, right? We have rise and fall of those currents due to temperature changes, which drives density. So we've got this dense, cold water falling, and we've got this hot, less dense water rising up. Okay, let's see if we can try and make not a mess and separate these. That worked much better than I thought that was going to be quite honest with you. Yay, me! All right, let's do this. So that's what we kind of talked about. That gets us started with our thinking. Let's do some student notes. First one, conduction. Don't worry about writing transfer of heat because that's already there. Why don't you, underneath conduction, say occurs when atoms vibrate against one another. So what I underline there, go ahead and fill in. Yeah.
Can I go to the health office?
Are you sick, man?
Maybe.
Oh my God. Yes, go to the health office. Grab the pass. Are you gonna like go with all of your things and not come back potentially?
Yeah.
Okay. I'm so sorry you don't feel well, but don't come back. Okay, well that makes no sense. All right, so this happens within a solid or between solid objects. I want to do a demonstration for this, so I need 3 people. 3 people. Okay, Asa, you're 1. I need 2 more people. Come on, Alex. Come on, Ethan. I need 3 people, for God's sakes. William and Ethan, get up here right now. It's going to be fine. You're not going to do anything other than stand here and move the way I'm telling you to move.
Yay.
Fine. God. So lame. Let's go. We got this. Actually, can we move up here so that everybody can see us on the screen?
Behind the desk.
Behind the desk. Okay, have you ever had a nice warm bowl of soup? Okay. You are the soup in the bowl. You are the boundary between the bowl and the soup. The soup is touching the bowl besides the bowl. The bowl is resting on the counter. The bowl is touching the counter. All right. So the soup is really hot. So since the soup is really hot, and this is an example of conduction, what are the molecules in the soup going to be doing if they're really hot? Right. They're going to be vibrating. They're going to be moving a lot, which means they're bumping into the molecules in the bowl, and the molecules in the bowl start doing what? Moving back and forth. And the bowl is resting on the counter, so eventually what are the molecules in the counter going to be doing? Move those shoulders, man. Moving. Okay, now you two keep moving. Eventually I eat all of the soup and the soup's out of the bowl. But the bowl is still hot, except eventually the bowl starts to move less and less because the soup is just not, you're still moving, right? And so now the bowl is cooled off, and if I move the bowl off the counter and I touch the counter, still move back and forth. Those molecules will start moving. Have you ever experienced that where you touch the counter where something hot was and it's warm?
Yes.
That's because the molecules are still warming, are moving. Now eventually the molecules slow down and it's all going to be back to like normal room temperature. You got me? That's conduction. Go sit down. Thank you very much. I appreciate that. So an example, if you wanted to write down an example, you can say a bowl of hot soup on the counter. Because on your piece of paper it says, give an example. A bowl of hot soup on the counter would be a great example. That's conduction. Those movement of molecules. Those molecules are excited because energy is inside of them and they bump into things and then it creates, it moves other things and makes them hot. That's what's happening here. You take a metal rod and you put it in a flame. Are you going to want to hold on to that for very long?
No.
No, because those molecules are like, and all of a sudden pretty soon it's going to get your hand, right? And it's going to be hot. All right, radiation. Again, you don't need to write down transfer of heat. You just say as electromagnetic waves. Write that down. Under thermal radiation. This is a picture of infrared. This is infrared energy. So what we're doing is we are looking using an infrared camera, and we can see the object that is giving out heat. Sunlight coming from our sun to our planet is also electromagnetic waves. So that's how, you go outside and you're like, oh, it feels warm. You just feel the warmth of the sun. That's electromagnetic thermal radiation. One of my favorite things to do is just like sit there and feel the sun. Does anybody else like the sun when you're out in it? It's very addictive. Give me your phone. Golly. Check out your success, Alfred. Someday when you're 26, we're going to bump into each other on the street. All right. So an example of that, you could say sunlight, if you want. Energy from the sun, that would be a good example. Infrared cameras, they use them at night for hunting, that would be a good example. Here is our electromagnetic spectrum that we did a lot of work in. We've got gamma rays all the way to our radio waves. And then of course the visible light spectrum is visible because that's the only thing we can see with our eyes. All right, next, convection. This is the transfer of heat from one place to another in a fluid motion, okay, by liquid or gas material. So that's our convection right here that's happening within the mantle. This is how a fireplace works. Does anybody have, or have you ever been to one of those houses where you've got that big old open fireplace in it? Yeah, we used to have one at our old house. They work great, except they draw, right, all of the heat goes up into the chimney. So if this was like a fireplace, and this was the opening to the fireplace, all of the heat goes up and then out to your chimney. Some of it will radiate out, but most of it goes up and it's replaced with cold air. You have to have what's called an updraft so that the smoke goes out and doesn't go into your house. And that updraft is really pulling all of the warm air out of your house and up your chimney. But it's the only way we can kind of like back in the day, that's how we warmed our houses. All right, so I guess for an example for convection, you can put mantle, if you want convection currents in the mantle. You can put how heat rises in a house, right? If you have, does anybody have these water heaters in your house? They heat up and it kind of goes up and then at the top it cools down and it falls back down. But when it's going up, that's why like the upper levels are so gall darn hot. Gall darn is not the damn word. So gall darn hot. All right, good? Yeah, lava lamp. Lava lamp would be a very good example of convection. I got my lava lamp out today. It's super hot. But what's in here is you've just got a light bulb. Wow, that's really hot. And you've got some wax that's in here. And the wax gets heated up by the light bulb. It's just like a regular, it's got a little cap on it and everything, a bottle cap. And then it rises up from the heat, gets up towards the top, which is away from the heat source, cools, and then falls back down. So a lava lamp would be a good example. $5.99 Walmart. All right, so here are some examples. You've got conduction, convection, and radiation. Conduction energy is transferred by direct contact. Things have to be touching, like a hot bowl of soup on the counter. Convection energy is transferred by the mass motion of molecules. So molecules are moving up and down, and again, due to that temperature difference, which drives density. And then radiation, energy is transferred by electromagnetic radiation. Good? Let's go ahead and draw some pictures. I think now we're down below. Heat. What did I do? Heat rises. Everything back here is like tied together with like rubber bands and string. What causes heat or liquid or gas to rise? Okay, we're going to go ahead and number this off, and this is where I'm going to add some information. So, heat, this is the first thing you're going to write, equals an increased motion, and I want to say in molecules. Molecules. Please add that. Increased motion in molecules. Okay, that's the first thing that happens. This then, number 2, is going to cause molecules to bump into each other. This makes them move apart. Remember, that's Newton's third law of motion. For every action, there's an equal and opposite reaction. If I am like floating around as a molecule and I bump into the wall, I'm going to fly off in the other direction. Then the third thing is this causes those molecules or that space to become less dense. If I was drawing this in a picture, I would be making some circles to represent my molecules, and I would be showing these things as moving around. So I'm going to go ahead and just kind of put these little marks on them to show that they're moving. So in your drawing example, if you could make some molecules that are kind of like wiggling around, that would be great. What? I know, we don't have to do all of them. I don't expect you to draw 1, 2, 3, 4, 5, 6, 7, circles. And then these are going to be bumping into each other and then flying away, right? They're going to be spreading out. When this mass spreads away from each other, it causes it to be less dense. And then this certain section of the fluid or air, whatever it is going to then rise up through the more dense area around it. Just like a hot air balloon. I love that lava lamp. It's very hypnotizing. Are we good? I used to have a student, Ella, I forget her last name, but her sister plays basketball this year. She's a freshman. Anybody know any basketball player with an older sister who graduated? What? What?
Yeah.
Molly, what's your last name? Yes, Ella McLaughlin. She would sit right there and she would just mesmerize would be the term. She loved that lava lamp. Just loved it. All right, cold sinks. Now, why? First of all, if you cool something off, it decreases the motion of the molecules. Cold decreases the motion of the molecules. So then what happens? Those molecules, so I'll say molecules settle in with or next to each other. The third thing, because of that decreased motion, that area becomes more dense. So if we're looking at a situation like this, these molecules would be all kind of settling in, not moving around. They would be pulling in towards each other, creating a more dense area in a surrounding area that might be less dense than it. So it sinks down. Do the numbers help? I'm very linear in that way. I need to know like the steps. It's all density driven by temperature in this case. Can I erase it? Ethan, let me know. Alex, why aren't you wrestling? Are you hurt?
I'm sick.
She did say that, didn't she? All right, we've got one last thing, the Earth's interior convection currents. We're going to label some of these and tie it all together as far as why the convection currents work the way they do. Number one, label that the lithosphere. That's the top. The lithosphere is the crust and the upper part of the mantle, the solid part of the mantle. At the very top, write the word lithosphere. So I guess in the lava lamp example, the lithosphere would be like, I don't know, the bottle cap. The next thing is the asthenosphere. That's the upper part, the lower upper part of the mantle. It doesn't matter, it's just the asthenosphere. It's right below the lithosphere. Does anybody remember what's below the asthenosphere? Mesosphere. And then does anybody remember what's below the mesosphere? Outer core. And then the inner core. Where's the heat? Right, just the core. Just write heat somewhere on the core. If you just want to say heat, hot, whatever you want on the core. That heat makes the mesosphere start doing what? Move. So I need you to make these little arrows. It makes the mantle in the mesosphere start moving up. And then, as it gets closer to the crust, what happens to its temperature?
Decreases.
Yeah, it decreases. Because the crust is actually cool. I hate that. It's not, it's cooler. It's cooler. Please just write cooler, not cool. It's cooler. So then, again, we have a density change. And now what's going to happen with that mantle? Yeah, that magma is going to start to become more dense and fall. Where it's going to begin to heat up again. And the process begins again. It's called a cycle. Now, this looks like it should go really, really fast, but it only goes about as fast as your fingernails grow. It moves super slow. It takes like millions of years for these convection currents to make a cycle. Super slow period of time. So we're going to go ahead today and look at an ancient supercontinent that a scientist named Alfred Wegener hypothesized happened 250 million years ago. And he didn't know any of this stuff that was going on below the surface, but he found evidence that showed the crust had been moving. And he called his theory continental drift. We're going to start looking at that connection between mantle and crust. Even though he didn't know what was happening, he had evidence to show that the crust was indeed moving. Whereas at one time, people thought, no, the mantle, or rather the crust doesn't move at all. The way that the earth is the way that it always has been. He found evidence against that. So if you could please get out your paper that says Reconstructing Pangea, we're going to go ahead and see if we can reconstruct that ancient 250 million year old supercontinent. It was called a supercontinent because all of the current continents that we have on our planet, all of the land masses, were connected into one big continent. It says, have you ever looked at a map of the world and noticed how some continents look like they could fit together like puzzle pieces? How many of you have ever put together a puzzle? All right, what are some things that help us put together a puzzle? If you're putting together a puzzle, what do you use for clues? Asa, give me one thing.
Pictures.
Okay, what do you mean the pictures? Like the
colors that might go.
Okay, the colors that might go together, the images on one puzzle piece compared to on the other. What is another thing that you can do? The corner pieces start in the corner. Yeah. What else? What about the shape of the piece? Right? If the shape of the piece, you look for one shape that fits into another. And so those are the two things that we're going to be looking for when we're trying to put together our puzzle. In 1912, a German scientist named Alfred Wegener noticed this, and he decided to find out why. Wegener was the first to hypothesize that the continents used to be connected and were still moving apart. Everyone at the time thought Wegener was crazy. They actually called him a crackpot. And it wasn't because they thought he was smoking crack. It was because, like a cracked pot, his ideas, they felt, does not hold water. And so they called him a crackpot. But he did have some evidence to support his claim, and we're going to look at that evidence today. Today we're going to examine this evidence and see how it supports Wegener's idea that the Earth's continents were once all connected to form a supercontinent called Pangea. So right now, could you please turn to the person next to you, look at this world map on the right, and tell me what land masses look like they might fit together. I'll give you a 10-second countdown, ready, set, go. One. Ethan, can you see anything that looks like it might fit together here?
The east side of South America and the west side of Africa.
Okay, so we could say South America and Africa. Let's go ahead and write that down. South America and Africa. Does anybody see any other continents that possibly could fit together? Is that it? Okay, well, we can start there. So yeah, it looks like South America and Africa fit right in. This little bump out right here looks like if you turned it just so, it could fit right into that space. So what you're going to do today is you are going to look for those kinds of clues, solving the puzzle to discover what the Earth looked like 220 million years ago. Number one, you're going to cut out the continents. Include the gray areas. What gray areas am I talking about? I'm talking about these gray areas. Okay? You got to cut these with it. So leave these attached. Because what that is, if we look at our key, this is landmass that is currently below the surface of our ocean. This is what's called the continental shelf. We need to keep those onto our landmasses. The landmasses above the sea level are the white landmasses. That's what we're used to seeing. Okay, but we need to make sure we leave the continental shelf. I have labeled the different pieces so you know what's Europe and Asia, which one's North America. And then I've given you, like Asa said, those clues on the edges of the puzzle pieces so you can see, are there any ancient deserts that would fit together? Is there a Plateosaurus fossil, or phytosaur fossil, or amphibians, or ancient basalt magma flows? See if any of those fit together to help you out. When you are satisfied with how you have your mat put together, show it to me before you glue it on the poster paper so that I can fix anything that might be wrong. I've given each group a big circle like this on blue paper. Please try to put your puzzle pieces inside. Okay, this represents the earth and our ocean, so we're going to do that. Does anybody have any questions? I'm shocked at how some of us can't cut well. So when you are cutting, remember it's easier for you to keep the scissors still, and what you're doing is you are rotating the paper, right? So that you can really get those nice cuts. And try to cut within this area. If you just try to cut with a little edge, you're not going to have very much control. Okay, so try to keep your scissors still as you cut, and it's the paper that you are moving. And then we're trying to get as close as we can to the edge. So slow, don't go so fast and say, I'm done. You are going to have lots of pieces that are connected, so please go in and cut those pieces so that we can have everybody cutting these pieces out. I need to check our time. We get out at 24, so we're probably not going to be able to get all of our pieces cut. I will go ahead and give everybody plastic bags, and we'll write period 3, and I'll say table 7, whatever. When you get over there, have somebody at your table put all of your names on the back of your blue paper so that we'll know where to start tomorrow. So we're going to go ahead and count off by 7s. You are 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All right, so looks like we're just going to have pairs of 2. Get up, get to your tables. The tables are labeled. I will get your bags so you can put your cut pieces in your bags. William, am I still recording? Okay. All right, people. We'll see you tomorrow.